Okay, in part 7 we talked about how a stellar core greater than 3 times the mass of the Sun is too heavy to be stopped by anything. It cannot be stopped by the degenerate electrons that slow down the collapse of a white dwarf. It cannot be stopped by the degenerate neutrons that stop the collapse of a neutron star. It is basically impossible to stop. And for all we can tell, the mass of the entire star falls to the very center of, well, falls to the very center of where it was and becomes what we call a singularity. The thing about the singularity is all the mass is concentrated in this tiny point. So if you look at the gravitational equation or you look at the escape velocity equation, it means you can get as close to the mass as you want. And the mass is the mass of at least 3 suns. And if you get really close, the escape velocity rises until it reaches the speed of light right here at 1 Schwarzschild radius. Again, a Schwarzschild radius is 3 kilometers for every solar mass of material. So at the smallest stellar mass black hole you can make is around 9 kilometers in radius. The bigger the mass, the bigger the black hole. The point is, this surface here, this imaginary surface in space, this location in space, is called the event horizon, because if you somehow cross the event horizon, you will never be heard from or seen again. Every piece of information that tries to come out of a black hole gets sucked back in because it cannot travel faster than the speed of light. That is one of the strange effects of a black hole. Let's talk about some others. First of all, the thing that's not so strange is that a black hole is only interesting when you're close to it. Well, I guess it's interesting even when you're not close to it, but the intense effects of gravity don't become apparent unless you are very, very close to it. If the sun were, for example, to magically turn into a black hole right now, it would certainly go dark, but other than that, we would not notice anything else. Basically, the Earth would orbit the black hole sun just as it does the regular sun, because the gravitational pull of the sun at the distance of the Earth's orbit would be exactly the same as whether it's a black hole or whether it's a star. So far away from a black hole, the gravitational effects are the same exact amount as you would get from a star of the same mass. Okay? So the Earth would orbit around the black hole sun just as it orbits around the sun now. However, if you get close to a black hole, there's a couple of different effects that are very, very strange. First of all, we talked about how it affects light, but it also affects time itself. Imagine throwing a clock into a black hole from just outside it, or imagine lowering a foolish astronaut from a spacecraft orbiting the black hole and lowering that astronaut into the black hole. That's not something you'd want to do. The wristwatch, or the astronaut wearing the wristwatch, would find that the time is ticking slower as he or she falls into the black hole. Clock would run slower and slower as it gets closer and closer to the event horizon. This is something called gravitational time dilation. In fact, as the watch fell into the black hole, you would not actually be able to see it fall into the black hole because the wavelengths of light reflecting off it would be stretched into the infrared and eventually into the radio regime and eventually be stretched into oblivion. So you wouldn't actually see the watch fall into the black hole. But if you could magically see the clock as it were about to cross the event horizon, it would seem to freeze there and stay forever with the sweep second hand at a particular time, never to advance to the next second. Time would slow down to 0 at the event horizon. Now, this would not be what the astronaut experiences. If the astronaut could survive the plunge into the black hole, which he or she couldn't, it would seem to happen all in regular time. In fact, they would see the rest of the universe suddenly traveling very, very fast. The astronaut might even see you in the spacecraft fly off and give up before he or she cross the event horizon. So that would be rather troubling. So again, the watch would seem to stop and hover at the event horizon, but if you were riding along with the clock, time would not slow down. It would take only a few seconds for you to crash into the singularity and become part of the black hole. I told you how light bent when gravity is strong. Well, in fact, if you're 1/2 Schwarzschild radius above the event horizon, photons can go into a circular orbit around the black hole. If you could just hover there, and good luck trying to get that to happen, if you could somehow hover there at that special distance, what you would see is the photons from the back of your head orbit around the black hole and eventually hit you somewhat distorted in the face. So basically you'd be able to see the back of your head whilst looking forward. Very, very strange. So if you could hover there, you could look parallel to the event horizon and see the back of your head. This is called the photon sphere, where photons can, you have to have exactly the right situation, but if you shot a laser beam exactly parallel to the event horizon, you could have that beam of light go into a circular orbit. Now, the other reason why you wouldn't want to ride along with the clock being thrown into the black hole is because on your way in, it would be very, very painful. Near the event horizon, the differences in strength of gravity over small distances is very large. There's something called tidal forces. Tidal forces are where gravity changes with distance. It's the type of thing that causes the tides. When the moon pulls on one side of the Earth with a stronger gravity than it pulls on the other, you get a stretching effect where the ocean gets stretched away from the Earth on one side, and the ocean gets sort of left behind a bit on the other side. So you end up with two high tides every day, because on the side facing the moon you get a high tide, and the side away from the moon you get another high tide when the Earth is pulled away from the ocean. However, that doesn't make any difference for you and I standing on the Earth or the moon, because we are so small. The gravity of the Earth is the same at our feet as at our head, whether we're standing on the Earth or the moon or any other normal object. I use the word normal loosely. But near a black hole, if you fell into the black hole feet first, let's say, the force of gravity at your feet would be so tremendously stronger than the force at your head that your head would get left behind and your feet would be pulled in more strongly, and you would end up getting stretched. This is something that sadistic scientists call spaghettification. Your body would be pulled apart, stretched into strands of spaghetti or something like that. Now, this would happen more if you jumped in feet first than if you belly flopped. You would still be stretched if you belly flopped, but it would take longer to spaghettify you. So I wouldn't recommend either. Stay away from black holes. They're dangerous, and no one will know where you went to. Okay, so here is my little drawing of this. Gravitational force is smaller at the head than at the feet, so you get a strong gravity pulling here, less of a gravity. It's still strong here, but it's less than here, and that differential in gravity stretches you out and spaghettifies you until you end up becoming part of the black hole. So, that's all fun stuff, but how do you actually find if black holes exist? Well, an isolated stellar mass black hole is almost impossible to detect. There are some ways of doing so. For example, if a black hole just happens to pass between us and a distant star, it will make that star brighten for just a short period of time. This is something called lensing or microlensing. When a black hole makes a distant star brighten, we can tell that it's there, but it's very difficult. You have to have exactly the right situation to have it happen. We do have robotic telescopes now that actually search the skies for these sorts of little brightenings. However, the way to really find a black hole is to find one that's not isolated, but is one that's in a binary star system. As we learned in an earlier chapter, binary star systems are not all that unusual, and close binary systems are not all that unusual either. So if you have a black hole in a close binary system with, say, a normal giant or supergiant star, the black hole will suck material off of the companion surface. When it does, the material from the surface of that star will swirl into the black hole like down a giant, strong bathtub hole plug of death, okay, or plug hole of death. So the material will fall into the black hole and swirl and swirl and swirl like a giant whirlpool. And in fact, the friction and heat created by this whirlpool effect of what's called the accretion disk will actually heat up the gas to such incredible high temperatures that it will emit X-rays. And we think that the vast majority of X-ray sources that we see in the universe are caused by black hole systems similar to this. Okay. One of the first confirmed stellar mass black holes is something called Cygnus X1. Cygnus X1 was the first X-ray source discovered in the constellation of Cygnus the Swan. And what we can see is a large supergiant star about 30 times the mass of the Sun that seems to be orbiting around an invisible companion. Now, by using orbital calculations, we can't know exactly what the mass of that invisible companion is, but we can get a limit on how small it can be. And the amount that the supergiant star is swirling around the invisible mass tells us that there's an invisible companion with a mass of at least 8 times the mass of the Sun. Now, we know that any stellar core greater than 3 times the mass of the Sun would collapse to a black hole and not be able to be a neutron star. And so this was the first really confirmed candidate of a black hole in our galaxy. Since then, dozens of similar black holes have been found, although not quite as many as we'd expect. There seems to be a dearth of regular stellar mass black holes, and astronomers are still searching for more. It's suspected that there are millions of them in our galaxy, but it's also expected that any X-ray source we see is caused by either a black hole or a neutron star sucking up material from a companion star. So at the very end, for the last minute and a half, let me kind of go over summarize the life cycles of stars. Okay? We talked about in the previous unit about the way stars are formed. They're formed from a cloud of gas and dust, a molecular cloud. They're born in batches, and you get a bunch of normal stars, low mass stars, or average stars. We'll just go with the average and the massive stars here. So if you have an average star somewhere between 0.4 and 8 solar masses, it will have a nice long main sequence life of billions of years probably, or at least a few 100 million years. And then will swell up to a red giant. And after it goes through its red giant stage, the core will collapse to a white dwarf. The outer layers of the red giant will be blown away into space as a planetary nebula. And the remnant, the remains that you get, is a corpse of a star, a retired star, only the size of the Earth. And that's what we call a white dwarf. On the other hand, if you have a massive star, something more than 8 times the mass of the Sun, you get a supergiant star. It doesn't really have to be a red supergiant star. It could be a supergiant star. It could be blue supergiant. And then when that core of that star reaches the iron stage, it becomes unstable. It implodes, which explodes the outer layers of the star. All the elements in the periodic table beyond iron are formed in those 30 seconds or so every century per galaxy. That makes the heavy elements of the universe. The remnant core turns either to a neutron star if that core is more than 1.4, then less than 3 solar masses. If it's greater than 3 solar masses, you end up with a black hole. One thing that fails to be shown in this diagram is the low average star, something we call an M dwarf or a red dwarf. These are very low mass main sequence stars. They basically burn virtually forever, but when they do give up their life, they're just going to go straight to the white dwarf stage. So you could put another arrow here, put red low mass main sequence star, and then ends up as white dwarf. All right, well, that's the end of this unit on stellar structure and evolution. We'll be going into galaxies next.